What if I told you that the vast empty space between us and the stars isn't what it seems? We often think of space as a stage. It is the backdrop upon which the grand cosmic drama unfolds. The stars, the planets, the galaxies, they all move through this pre-existing void. But what if space itself is not fundamental? What if it is built from something much stranger, something happening at the deepest level of reality? This idea might sound like science fiction. Yet it is a concept that physicists around the world are seriously exploring. It challenges our most basic understanding of the universe and our place within it. It suggests that everything we see, from the chair you are sitting on to the most distant quasar, is connected in a way we are only just beginning to grasp. At the heart of this revolutionary idea is one of quantum mechanics' most baffling phenomena. It is something Albert Einstein famously called spooky action at a distance. He was talking about quantum entanglement. Imagine you have two tiny particles linked together in a special way. You could send one particle to the other side of the galaxy. The other remains here on Earth. The instant you measure a property of the particle here, you instantly know the corresponding property of its distant twin. It's as if they are communicating faster than the speed of light, which should be impossible. This connection is not just a theory. It has been proven in countless experiments. This strange, invisible link seems to defy our common-sense notions of space and time. Think about the screen you are looking at right now. It appears as a smooth, continuous image. You see pictures and text and colors. But if you were to look incredibly closely, with a powerful microscope, you would see that the image is not smooth at all. It is made of millions of tiny, individual dots called pixels. Each pixel has its own properties, like color and brightness. The continuous image you perceive is an emergent property. It arises from the collective behavior of all those individual pixels. The image itself isn't the fundamental thing. The pixels are. Now, let's apply this idea to the universe. Physicists are beginning to suspect that space and time might be like that screen. So if space is not fundamental, what is it built from? The incredible answer might be from relationships. The most fundamental layer of reality may not be made of tiny particles or vibrating strings. It might not be made of any stuff at all. Instead, it could be a pure network of information, a pattern of entanglement connections. These connections are the building blocks. Think about it this way. The value of a word comes from its relationship to other words in a sentence. The word blue has no inherent meaning on its own. Its meaning emerges from its context and its difference from red or green. The reality is the network of relationships. In the emergent space picture, the universe is similar. The fundamental entities are qubits of quantum information. How much information does it take to describe our universe? You might think it depends on its volume. To describe a bigger region of space, you would need more information. This seems obvious. But a mind-bending idea from physics, called the holographic principle, turns this intuition completely on its head. It suggests that the information needed to describe a volume of space does not depend on the volume itself. Instead, it depends on the surface area that encloses it. This is like saying that everything you need to know about the inside of a can of soup is written on the label on the outside. It's a strange and powerful concept. This idea first came from studying black holes. Physicists like Jacob Bekenstein and Stephen Hawking discovered something remarkable. The amount of information or entropy that a black hole can hold is proportional to the area of its event horizon. This link between entanglement and geometry led to one of the most provocative and exciting ideas in modern physics. It's a simple-looking equation with profound implications. ER equals EPR. This is another one of those acronyms, but it represents a powerful conjecture that connects two of Einstein's biggest ideas. On one side, we have EPR, which stands for Einstein, Podolsky, and Rosen. They were the physicists who first wrote about the paradox of quantum entanglement, the spooky action at a distance. They worked together to find a mathematical solution in general relativity that we now call an Einstein-Rosen bridge, or more famously, a wormhole. A wormhole is a theoretical shortcut through spacetime, a tunnel connecting two distant points. So the equation ER equals EPR, proposed by physicists Leonard Susskind and Juan Maldacena, makes a bold claim. It suggests that these two ideas are one and the same. So far, we have journeyed through some truly mind-bending theories. We've explored the idea that space is a hologram and that wormholes and entanglement are two sides of the same cosmic coin. But this is physics, not philosophy. Theories are only as good as the evidence that supports them. The crucial question is, can we test these ideas? Are there any real-world experiments that can show us whether space truly is built from quantum entanglement? The answer is a tentative but exciting yes. Scientists are not just scribbling equations on blackboards. They are in laboratories around the world, trying to find the first experimental whispers of this new reality. While some scientists look for evidence out in the cosmos, others are trying a different approach. They are trying to build their own toy universes right here on Earth, not with stars and galaxies, of course, but with special materials and quantum computers. These are called quantum simulations. The goal is to create a system of quantum particles, like atoms cooled to near absolute zero, and manipulate their entanglement in a controlled way. Perhaps the most compelling evidence for a deep link between entanglement and spacetime comes not from a lab, but from a profound cosmic puzzle. This is the black hole information paradox. According to Stephen Hawking, black holes are not completely black. They slowly evaporate over immense timescales by emitting a faint glow of particles, now known as Hawking radiation. The problem is that this radiation appears to be completely random. It contains no information about what fell into the black hole. This creates a crisis for physics, because a fundamental rule of quantum mechanics is that information can never be destroyed. Imagine you burn a book. In principle, if you could collect every particle of smoke, every bit of ash, and every photon of light, you could reconstruct the information in the book. The idea of emergent space offers a revolutionary solution. Remember the holographic principle? The information about the inside of the black hole is encoded on its event horizon. The new insight growing from the ER equals EPR idea is that the Hawking radiation particles that leave the black hole remain entangled with the particles still inside. This elegant solution saves quantum mechanics. The information gets out, not written directly in the radiation, but hidden in its entanglement pattern. Looking to the future, what discoveries might lie just over the horizon? The quest to understand quantum gravity and the nature of spacetime is driving some of the most ambitious experiments ever conceived. On the one hand, we have particle accelerators like the Large Hadron Collider, pushing the boundaries of high-energy physics, searching for new particles and forces that could provide clues about the universe's fundamental structure. On the other hand, we have incredibly sensitive cosmological surveys, mapping the faint afterglow of the Big Bang and the distribution of galaxies with breathtaking precision. The most exciting developments may come from the world of quantum computing. As these machines become more powerful and sophisticated, our ability to simulate quantum gravity will grow exponentially. Today, we can simulate a handful of entangled qubits to create a toy wormhole. In the future, we might be able to create much more complex holographic simulations. We could build virtual universes in silicon and watch them evolve. These quantum laboratories could become our primary tool for exploring the fundamental laws of nature in a way that was previously unimaginable. Ultimately, a complete theory of quantum gravity, one that successfully unites Einstein's relativity with quantum mechanics, would change everything. It would be the final chapter in a search that began with Newton. Such a theory would not only describe the origin of space and time, but it could also answer some of the deepest questions we can ask. What really happened at the Big Bang? What is at the heart of a black hole? A final theory might provide us with the ultimate cosmic blueprint, the source code of reality itself, revealing how the universe began and why it has the properties it does. We began our journey with a simple, yet profound question. Is the space around us truly fundamental, or is it woven from something deeper and far stranger? We've traveled to the very frontiers of human knowledge, exploring an idea that could reshape our understanding of everything. The notion that the vast, three-dimensional expanse of our universe emerges from the ghostly connections of quantum entanglement is perhaps the most revolutionary concept in modern physics. It suggests that the reality we perceive is like a grand cosmic hologram projected from a network of pure information. The spooky links that so troubled Einstein might not be a weird feature in the universe. They might be the universe itself. This is more than just a mind-bending philosophical puzzle. It offers a tantalizing bridge between the two great pillars of physics: Einstein's general relativity, which governs the cosmos at large, and quantum mechanics, which rules the world of the small. For a century, these two theories have stood apart, powerful but incompatible. The idea that spacetime is built from entanglement provides a common language, a dictionary to translate between the geometry of gravity and the information of quantum bits. Solving deep mysteries, like what happens inside a black hole or how the universe began, may depend entirely on our ability to grasp this profound connection between them. The quest is far from over. We are like early explorers charting a new continent, with only a few tantalizing glimpses of the vast landscape that lies ahead. What we have learned is that the cosmos is far more interconnected and mysterious than we ever imagined. The space that separates us may be an illusion, a macroscopic habit woven from an intricate web of invisible, instantaneous links. Every particle, every star, every galaxy could be part of a single, unified quantum system, bound together in a spooky embrace. The future of physics promises to be an extraordinary adventure. As we continue to probe this hidden fabric, we may find that the deepest truths about the universe are not written in the stars, but in the connections between them,